Hey everyone, I'm Claire. I'm an AWS software engineer in developer tools. And today I'm going to talk about continuous integration best practices for software development teams. So before we jump into talking about continuous integration, I first want to show you a couple of sample chats that I've seen on teams that aren't using best practices for continuous integration. So on this one, we're seeing that the team has a broken build. A bunch of developers on the team are blocked by this build. They can't do anything locally. They can't work on their changes. So someone's got to go off and fix that. Here we're seeing that the team has a test stack. So they've gotten some code reviewed and have tested it locally, but unfortunately it fails on their test stack. And so everybody else's changes are blocked behind this broken change going out to production. And finally, what we're seeing here is someone seeing some test failures locally. We've all got different local development environments. Someone claims that they tested their change before they pushed, but it's not working for everybody on the team. So we're going to look at some best practices to help you get out of these situations that you're seeing in your team chat rooms and that are affecting your team's productivity. So today I'll start off with an introduction to continuous integration. I'll talk about the continuous integration tooling that I use, and then I'll walk you through 3 techniques for continuous integration best practices. And then we'll wrap up with some final thoughts. So first, introduction to continuous integration. Continuous integration means a lot of different things to different people. So for the purposes of this webinar, I'm going to define it like this. First, developers regularly check in code to a shared central repository. So mostly in the examples that I use, I'm talking about a master branch on a Git repository. Second, automated checks run regularly against that shared code base. And finally, developers get the feedback from those automated checks about their code. And continuous integration is really continuously going around this wheel, continuing to get better at checking in code, running those checks, and getting feedback back to the developer. But why does continuous integration matter? So I break this down into 3 different themes. One is bugs. So with continuous integration, you find bugs earlier and you fix bugs faster. So according to the 2017 State of DevOps report, teams that have adopted continuous integration and other DevOps best practices see a 5 times lower change failure rate. So that's really great for these teams that have adopted these practices. Second theme is delivery. So teams on CI deliver faster and they deliver more often. These teams have a 440 times faster time from commit to deploy. So from the time that a developer makes that commit to the time it gets out to production, 440 times faster. They also have more frequent deployments. So 46 times more frequent deployments. So what we're talking about for these teams is they go from deploying, once a quarter, maybe once a week, down to hours. And the time that it takes for a particular change for a particular developer goes down from months or weeks down to hours. The final theme here is really the team. So continuous integration unblocks developers to do what they love doing best, which is coding. So it unblocks developers and it grows their skills faster because as they're going around that continuous integration wheel, they're getting feedback to help them make better changes in the future. So this results in happy teams. 44% of these teams, they get more time to spend on new features and code. So these teams are super happy because they're getting to do what they love. So let's look at the continuous integration tooling that I'm using and the techniques that I'll talk about. In order to illustrate these techniques, I've created this sample application, the simple calculator service. So here it's showing it's doing pretty simple multiplication, nothing special. The tools that I'm using here, looking at the continuous integration wheel, I'll be the developer as we're walking through. And I'm going to check in code to a couple of different repositories. I'll show you what this looks like on AWS CodeCommit, and I'll show you what it looks like on GitHub as well. I'm going to run checks using AWS Code Build. So Code Build is going to run all of the automated checks for the CI techniques. The way that we're going to orchestrate the continuous integration wheel is with Amazon CloudWatch events. So there are a lot of different tools out there that can help you to tie together your continuous integration wheel. Examples include AWS Code Pipeline and Jenkins, but I wanted to take it down to the basics and really show you how you can tie these together for your own custom continuous integration wheel. So I mentioned that I'm going to use AWS Code Build for all of the automated checks for continuous integration today. If you've never seen Code Build before, it is a fully managed build service. It is continuously scaling. What that means is that it never queues up your builds. You can throw it as many builds as you want, and they will all run at the same time. It's pay as you go. So you only pay for the build minutes that you use. And that means that you can throw a bunch of builds at it. They can all run at the same time. And then once those are done, that's all that you pay for. And finally, it's extensible. Pretty much anything that you're doing on your laptop to build or test your code, you can do in Code Build. It's super flexible. There's a couple of concepts that will come up during the techniques that are concepts that are core to Code Build. One is the build project. So what I'm showing here is the AWS Code Build console, and this is the list of build projects that are in my account. So let's drill into one of these build projects. The build project is really a place to store the configuration for how to build your code. So there's a couple of different configuration items here. One is the source code. So here I'm using CodeCommit. And I've got my node calculator service repository. Next is going to be the build specification, which is essentially the commands to run to actually build my code. And finally is the image. So every code build environment is a Docker container. There's a set of official code build environments. Here I'm using the Node.js 4.3.2 official environment. But you can also provide your own build environment in the form of a Docker image. So if you have special build tools and testing tools, or a complex combination of tools, like you have a Node.js and Java application, you can combine those together into one image and use that as your build environment with Code Build. This is a sample build spec. So I mentioned the build specification before. This is where you specify just the commands to run to build and test your code. So there's a couple of different sections here. First, the phases section, you'll see the install and build. Code Build has a set of phases that you can specify install, pre-build, build, and post-build. And for each of these, you can specify what commands you want Code Build to run. And then Code Build will tell you success or failure for each of them. So you can really narrow in on what failed during your build. So here I'm using npm install and npm test. This is a Node.js application. And then at the bottom, the second section is the artifact section. So Code Build will take care of uploading your artifacts for your build into S3. And here I'm using a wildcard for files. So in the build environment, it's going to take all of my source code, all of my dependencies, my node modules, zip that up and put that in S3. But you can specify any individual files that you need as artifacts for the build to deploy to production later. So once you have the Code Build project configured, you'll start a build. And this is the list of builds that I've been running in my AWS account. And I'll focus in on one of these. So this is a successful build in my account for my node calculator service. These are the all of the phases that ran. So I mentioned that you can specify commands for install, pre-build, build, and post-build, and these are the full set of phases that run, and it's telling me that all of them succeeded. And then as I scroll down more, I'll see the build logs, so I can see all of the unit tests that ran for my build and that they were all successful. These are streamed out to CloudWatch logs from the build, and then they're also shown here in the Code Build console. Code Build launched a little bit over a year ago, and we've been pretty busy since then. So there's been a couple new features. One is that you can now build source from bitbucket.com and GitHub Enterprise, in addition to building from S3, from AWS CodeCommit, and from github.com. You can now add builds to GitHub pull requests, so you can automatically kick off builds from a pull request. You can build inside of your VPC, which I'll show you an example for later. You can use secrets from Amazon Parameter Store, so you can load secrets like a database password into your build environment securely. And finally, you can cache libraries in S3 now with Code Build, and I'll show you an example of that as well. So let's jump into these 3 continuous integration best practices. For each one of these, I'll give you a definition, how to implement it, what your team will say in their team chat, and then how to level it up and fully take advantage of the technique. So getting back to the continuous integration wheel here, as I started thinking about this continuous integration for teams and walking through these different techniques, what I started thinking about was how this wheel starts spinning faster and faster as teams get better at continuous integration. And so I've broken down the 3 techniques into 3 different velocities that teams are moving at when they're developing their changes. So we're going to talk about nightly checks, branch level checks, and then pull request checks. So let's look at this team that has no continuous integration at this point. They have a release deadline coming up and they don't integrate on a continuous basis. And so they haven't done a full build since their last release 3 months ago. So they are in for a world of hurt once they try to actually build and integrate all of their changes together for the next release. So the first technique is nightly checks. What I mean by that is you run a full build and unit test every night to make sure that your application still compiles and that your tests still pass. In order to implement this, I'm going to use CloudWatch events like I talked about for the continuous integration glue. In CloudWatch events, you can set up a schedule. So we're going to set up a schedule to run this nightly, and that's going to trigger a code build. So here on the CloudWatch events console, I have a rule configured that simply has a cron expression. So this is going to run every day at 8, and that's going to trigger off a code build. This is an example of a build that failed that was kicked off nightly. And then specifically the build phase failed here. So when I look at the build logs, I can see that one of my unit tests failed. So at this point, I know the master branch is unhealthy. I'm probably blocking my team members. They're not able to build locally, and we're not able to push anything to production at this point. So as long as we do this every night, we have a general idea of how we're doing as a team and how the master branch is doing. Let's talk a couple of speed boosts here to fully take advantage of nightly checks. We're going to talk about email notifications and then automating code-based maintenance to fully take advantage of nightly checks. The first is email notifications, right? So one of the problems with nightly checks is if no one actually notices that the nightly check failed. One of the things you'll start to see is that the nightly check fails for a week at a time and no one notices. And so it's not really doing you any good at that point. So in order to get daily email notifications about failed nightly checks, I'm going to use simple email service to kick off an email once I get a failed notification from Code Build through CloudWatch events. So here in the CloudWatch Events console, I have a rule set up to only pay attention to failed and timed out builds. So I don't really care about the successful builds, being notified about them to my email, but I definitely want to know about failed builds. And this is a sample of the email that I'm sending to myself when the build, the nightly build fails. And specifically what I really like here is that I'm getting a little snippet of the log so I can see really quickly what unit tests failed, what was going on in the build that triggered this failure. So the second speed boost is automating code-based maintenance. One of the problems that we see on a lot of teams is struggling to keep up with library upgrades. So we want to keep up with the latest patches and security fixes in library upgrades, but developers don't really want to do it on a regular basis. And part of the reason for that is that it's pretty difficult. So for even just my simple calculator service, I only have these two dependencies. I have a web service framework and a number formatting library. But what that actually turns into is these hundreds of dependencies that I actually have through those two dependencies. And so keeping this list of libraries up to date is a huge pain. And it's really a difficult task for engineers to do when they really want to be working on new code and new features. So I've set up automated upgrades for my libraries in CodeBuild. So I do, again, a CloudWatch event schedule that kicks off nightly. That's going to kick off a CodeBuild build. Instead of, in this build, compiling and testing my code, first I'm going to upgrade all of my dependencies and then rerun my unit tests. And if all of those unit tests pass, I'm going to push the change for all of my updated libraries into CodeCommit. And so this takes off a lot of that heavy lifting for engineers so that they can focus on new code and new features. This is an example of my build spec for my automated upgrades build that I kick off every night. So here I'm regenerating an npm shrink-wrap file, which is similar to gem file locks or PyPy locks in Python and Ruby. And at the end of it, I'm simply adding that shrink-wrap file to my CodeCommit repository and pushing that to CodeCommit. So here on the CloudWatch Events console, I have a rule that just kicks off every day. I do this every day to update my npm dependencies. This is an example build that got kicked off, so this succeeded. And now in my CodeCommit repository, I see a new commit from my shrink wrapper bot, which ran in CodeBuild, that updated all the npm dependencies. So we've got a couple of speed boosts here, but it's not quite enough for this team. So they're getting the email that last night's build failed, but someone could have pushed that broken change anytime yesterday and blocked the team. So to summarize about nightly checks, in order to implement it, we run a build every night, let's say at midnight, using CloudWatch events. The feedback loop here is pretty high, so 16 to 24 hours. And that's based on if someone pushed a change, let's say between 9 and 5 p.m. yesterday, no one's going to really know that the build is broken until 9 a.m. the next day, when they get the email that the nightly check has failed. And the team impact here is pretty high. So broken code on the master branch can actually block that team for entire days. You end up getting into this vicious cycle where you pushed a broken change, nightly build fails, you try to go and fix it, you push it again, another nightly build fails, and you get into this cycle of trying to fix it and having this really long feedback cycle. But we looked at a couple of speed boosts here for nightly checks. One was email notifications in order to actually pay attention to the fact that the nightly build is failing, and then automating some of that code-based maintenance to take that off of the engineering team. Let's move on to branch level checks, technique number 2. We're getting a bit of a speed boost here, upgrading to the car. And what I mean by branch level checks is that we'll run a full build and unit tests every time someone pushes a new change to a branch in the source code repository. So let's look at how you would implement that on CodeCommit. So CodeCommit also emits CloudWatch events. So we're going to take advantage of that to kick off a build anytime someone pushes to the CodeCommit repository. Here on the CloudWatch events console, I have a rule that specifically pays attention to CodeCommit pushes only to the master branch. So I've decided that that's the branch I want to keep healthy. Let's step through what would happen for a sample change to the master branch. Here I've pushed a add subtraction test change to my CodeCommit repository, and that build failed. So at this point, the master branch is unhealthy. If someone pulls down the latest changes, the build is going to fail for them locally too. And then quickly, but hopefully before I've blocked any of my teammates, I push a fixed subtraction test change to my CodeCommit repository. And that has kicked off another build, and that build succeeded. So now I know that the master branch is in a healthy state because of this build. So let's look at how to do this on GitHub. So a team member is going to push into a GitHub repository. CodeCommit integrates with GitHub webhooks. So the GitHub push is going to start a code build, and code build will report the status of that build back to GitHub. For the code build project, I simply check off webhooks for my GitHub source, and that will rebuild my repository every time a change is pushed to the repository. This is looking at my repository settings on github.com. You can see that the payload URL for the webhook targets code build. And on the bottom, I'm only paying attention to the push event for this webhook. So I pushed the same add subtraction test change to GitHub, and you'll notice the red X next to it. That's because a build was triggered for code build, and the failed build was reported back to GitHub. And now I have a visual marker that the master branch is unhealthy in this repository. So then I push my fixed subtraction test change, again, hopefully before I blocked my team members. That triggered another build, which got reported back, and that was successful. So now I have the nice green check for my repository. Let's look at a couple of speed boosts for branch level checks to make sure we're taking full advantage of this technique. The first is going to be Slack notifications, and then we'll also look at caching. So for Slack notifications, again, one of the problems that we saw even with nightly checks was making sure that we're paying attention to the fact that the builds are failing for our automated checks in our CI process. So here, someone broke the build, but no one paid attention to the fact that the CI build actually failed, and several hours passed before that got resolved. So we're going to take advantage of Slack notifications to get notified immediately in our Slack channel that the CI build has failed. So we're going to use the CloudWatch events that are emitted by Code Build to post into our Slack channel using a Lambda function. This is a similar CloudWatch event rule that I used for email notifications. Again, just paying attention to failed or timed out builds to make sure we're not flooding our Slack channel with successful build notifications. And here, this is a sample Slack channel where I have a notification for both the CodeCommit failure, which we walked through for branch level checks, and the GitHub failure. So at this point, I know I need to go unblock the build before I'm blocking my teammates. So now let's talk about caching. The other way to speed up the feedback loop for branch level checks is going to be by speeding up the build itself. So if you think about a build that takes 2 hours to run, that means that our feedback loop is at least 2 hours before we know that the master branch is unhealthy. And going back to this massive mega list of dependencies that I have, this can take a long time to download all of these dependencies. So in Code Build, your build has a fresh environment every time in a Docker container. And so you have to re-download your dependencies every time, which you don't normally have to do on your laptop, for instance. So caching can help to reduce this time quite a bit. With caching, you store some of your dependencies or any other assets that you want to cache. CodeBuild will store them for you in S3. So at the beginning of the build, it will download from an S3 bucket, wherever your cache is stored. You can, on top of that, install all the rest of your dependencies. So when you're using caching, you only have to install from the NPM registry whatever's changed, whatever's not yet in your cache. And then at the end of the build, it will update the cache in S3. So this can save quite a bit of time for builds that spend a lot of time re-downloading these dependencies every time. And for my build in particular, since I'm using Node, I simply have to cache my Node modules folder, and this gets added to my build spec. And then CodeBuild will take care of the rest of making sure that that's available for my build. As part of the project, I turn on the cache settings. So I'm selecting a S3 bucket and then a path prefix where my cache will be stored. And then previously for my build, I have a pretty simple application here. It used to take about 30 seconds for me to install all of my NPM dependencies. And that's for a really, really simple application with only those 2 dependencies. And with caching, I'm able to get that down to only 4 seconds. So 30 seconds to 4 seconds doesn't sound like a big deal, but it's a huge percentage increase. And so as you have a more and more complex application with more dependencies and larger dependencies and assets, you can see some real time improvement using caching. So we can now have pretty good confidence that we have a healthy master branch, or at least we know whether the master branch is healthy or unhealthy after every push. But we still have a problem where you can still have these master branch builds failing. And the problem comes when your teammate is testing their changes locally before they push. They have pretty good confidence that this change works, but then it fails in Code Build. And it fails on other people's laptops or development environments. And so we're going to talk about how to move past failures like this as well. So for branch level checks, in order to implement it, you simply run a build every time new code is pushed to a branch. So we saw pushing to the master branch. The feedback loop is far better than for nightly checks with branch checks. So the feedback loop shortens from that 16 to 24-hour cycle down to simply the time that it takes to build the code. Now this is, of course, at a minimum, because you do have to pay attention to whether you have to pay attention to the fact that the branch check actually failed. But it is in terms of the team impact, it is a much shorter cycle. You can still have broken code that blocks the team. So if it takes 1 to 2 hours to go and fix whatever is broken on the master branch, that can be an impact to your team. That is far better than nightly checks. And we saw a couple of speed boosts to take full advantage of branch checks. We looked at Slack notifications and we looked at caching. So let's move on to the final technique here, pull request checks. So again, we're getting a speed improvement. We're upgrading to a train. And with pull request checks, we run a full build and unit test every time someone creates a pull request to get code reviewed by the team. So let's look at what that looks like on CodeCommit. CodeCommit pull requests was launched in November of last year, so pretty recently. And with the CodeCommit pull request checks, the team member is going to propose a CodeCommit pull request. That's going to emit a CloudWatch event. So we can use that CloudWatch event to start a code build. Then we're going to use, going back the other way, use the code build CloudWatch event to trigger a Lambda function that will comment on the pull request in CodeCommit and give feedback to the author of the pull request. So here, walking through an example, I'm going to use those same broken subtraction test changes that I use for branch level checks. But this time I'm going to create a pull request for those checks first, for those changes first. So here I have a subtraction feature branch that I've added my change to, and I'm going to create a pull request. So walking through creating the pull request, I have this change. It's a broken change. The unit tests are definitely going to fail, but I don't know that yet. So now the pull request is created, and my team members are free to review my changes at this point. But what's great about pull request checks is that my teammates are going to get a notification that a build is in progress for this pull request. So now a build has been kicked off for this pull request. It's in progress, and then the build failed. So at this point, my team members also have this indication, in addition to me, the author of the pull request, that something's wrong with the changes that have been proposed. So this is actually really great for the productivity of my team as a whole, in addition to me as the author getting feedback, because they can sort of ignore my pull request until I go and fix my changes. And they spend less time reviewing broken changes, reviewing low quality code or the unit test doesn't pass, in addition to giving really quick feedback to the author. So here in the comment that the pull request bot left on the pull request, again, and like I did for the email notifications, I get a little snippet of the logs, which I personally really like because I'm able to see immediately what are the unit tests that failed, what's going on in this change that would have caused tests to fail. So I spend a lot less time going and searching for why the build failed. So then, just like I did for the master branch checks, I push my fixed subtraction test change to the feature branch, and that automatically updated this pull request. So the pull request is now updated. I have new changes here. A new build has been kicked off, so now a new build is in progress, and that build succeeded. So at this point, my team members are able to get some clear feedback that this code review is ready for review, and not have to worry about me as the author breaking the master branch. So let's quickly look at what this looks like on GitHub. So a team member is going to propose the same change to GitHub pull request. Through the webhooks integration, that's going to start a code build, and then the status of that build will be reported back to GitHub. Here on the github.com side for my repository settings, we're using the same webhook that's targeting code build. But this time, the only difference is that instead of just paying attention to the push event, like we did for branch level checks, we're adding the pull request event. So every time there's a new pull request or updated code for the pull request, we'll see a new build being kicked off. Again, I have a subtraction feature test branch that I've pushed a change to, and I'm going to create a pull request for that. So here I have my pull request add subtraction test change. I'm showing the add subtraction test commit here. And that has kicked off a build which shows up as a check in the GitHub pull request. So it's showing that a build has failed for my code build project. And my team members can see that, that the checks have failed and sort of ignore my pull request while I'm fixing this change. Then at the top, I've pushed my fixed subtraction test commit to my feature branch that automatically updated my pull request. A new build was kicked off in code build, and that build succeeded. So at this point, I get the nice all checks have passed flag in GitHub, and my teammates can have confidence in this change and hopefully merge my changes. Let's talk about a couple of speed boosts for pull request checks. So now that we have pretty good confidence in running the unit tests and compiling all the code in the pull request, we're pretty sure that the master branch is going to stay healthy. But what we want to avoid is now getting farther into the deployment cycle, so deploying to the test stack, for example, and having that fail. So in order to speed up that time from commit to deploy, we're going to add more checks to the pull request. Make sure that all of the checks that we're going to run between merging that to the master branch and deploying that to production can actually run inside of the pull request. And then as we start to add more checks, we can parallelize those checks. So what we don't want is running all of those checks in a single build, and then all of a sudden your build is back to taking hours and hours, and you don't get a lot of feedback from that pull request until much later. So we'll look at how to parallelize the pull request checks. So here we saw this TeamChat before, but what's happening is deployment to the test stack failed, even though we have a healthy master branch and people can build and run the unit tests. The integration test failed in the test stack, and so we're still blocked for getting things into production. So let's look at an example integration test here. As I talked about before, CodeBuild recently released support for building inside of your VPC. So one example that I'm going to walk through is working with an Elasticache cluster, a Redis cluster in my VPC with an integration test in CodeBuild. So here I have my node calculator repository build project in CodeBuild, and this test failed. So I tried to run integration tests in my build, and unfortunately this failed. So I can look at the logs, and what I'm noticing here is that my Redis client is broken. So this is a really great example of how locally your test could pass if you're using an integration test against a Redis cluster, but potentially you might be running against, locally, you might be running against the Redis cluster that's in your VPC. You might be running against a Redis client, a Redis cluster that's just local. But you want to make sure that you are making sure that you actually run against a real Redis cluster in your VPC that you would, similar to what you would use in production for your integration test. And so there's some problem here where this probably worked for me locally, but it's going to fail in an integration test. So now I have a new integration test project. And for this one, I have VPC turned on. So I've selected my VPC where my Redis cluster is, selected the subnets within that VPC, and a security group for the build. And this build has succeeded. So what I can see at this point is I have an environment variable that's specifying the Redis host that I want to use. That's my Elasticache cluster. And then the build phase succeeded this time. So here in the logs, I can see that it actually connected to my private Elasticache cluster and was able to set variables into the cache. Let's look at parallel builds. What I want is to be able to run my integration tests in parallel with my unit tests and get all of those checks showing up in the pull request. So again, what you don't want is for the pull request checks to take hours and hours. Otherwise, it's going to be a really long time before you get feedback. So with parallel builds, specifically, I'm going to show you how to do this in GitHub. We have this pull request that I opened up for add subtraction tests. I can start out with my normal unit tests project that's going to run my unit tests. But I can also run static code analysis. I can run my integration tests. So all three of these are running in parallel. Here my unit tests actually passed, but static code analysis against something like SonarQube failed, and my integration test failed. So if I were to push this to the master branch now, the master branch would appear healthy because the unit tests are passing, but the integration tests are going to fail in my test stack. So here we have the final TeamChat. They've achieved nightly builds, pull request checks, branch level checks, and they are super happy with their results with continuous integration. So to summarize for pull request checks, in order to implement it, you run a build while the code is actually still in review in that pull request. The feedback loop here is about the same as branch level checks. So for the author of this code, it is still the time that it takes to build that code. However, the team impact is much better than branch level checks. The broken code doesn't block the team this time. They're able to see that the checks have failed before they actually merge it to the master branch. And the speed boosts that we looked at are integration tests to do more and more checks against your code base before it gets merged to master, and then parallel builds to speed up that process. So final thoughts here. We looked at nightly checks, branch level checks, and pull request checks. These all had a different velocity as we were adding new best practices for the team. We looked at a few speed boosts. If I were to summarize these, number one, automate the boring stuff. We looked at library upgrades, but you can find other needs for automation in your specific application. We looked at surfacing more failures. So making sure that the feedback loop was small by surfacing these failures to the team faster. So we did that with email and with Slack. And third, we looked at checking faster. So running these checks faster and faster. We looked at caching to make the speed of the build as fast as possible, and then parallelizing builds to break up the build into parallel tasks. And then we looked at checking more. So making sure that we're running more and more deeper checks against the code base, not just unit tests in that pull request phase. So we looked at running integration tests. And so finally, the advice that's really I want you to come away with is that starting somewhere along this wheel, implementing some kind of practice that starts you getting spinning around the wheel is the most important part here. And then over time, you can spin faster and faster by adding best practices, adding new processes to your team for continuous integration. So that's what I have for you today. You can check out the sample application that I used for all of the examples on github.com that has all the build specs and continuous integration tools that I walked through today. So thanks so much for being here for this webinar.